This is question 9.10 of the FEEG1003 workbook from the 2015-16 academic year. So question 9.10 again concerns conservation of energy. So we're modelling this as an inviscid problem, so we're applying Bernoulli's principle. What we have here is a carburettor, which is a thing back from the olden days that was used to mix fuel and air in an internal combustion engine. What we do, we have a tapered duct here, and we accelerate air, so we increase the velocity, and that basically then draws or sucks fuel from a sump, and then the fuel and the air mixture, so the fuel and the air mix in this region and then into the cylinder, compressed, ignited, creates energy. The key issue, we have air of a known velocity at the inlet. We don't know what the velocity is at the outlet, and we have an area ratio, so we don't have an absolute value of either area at this point. So once again, we'll have two unknowns in Bernoulli. I think that's fairly obvious before writing it out. A key part to this question is working out where you can apply Bernoulli between, and you have to make sure that you apply it between 2 points on a streamline, and that's very important. So the question, we're going to tackle it in two parts. Because we know the velocity at the inlet and we have an area ratio, we can, I think, hopefully you can see, we can work out the differential pressure in this duct. So between here at the inlet and here at the outlet. So in this region where the area is known and fixed, we can apply Bernoulli. Okay, so we'll start with these two points here. So as the duct is level, we can write a shortened form of the equation. So we want to work out P1 minus P2, so the differential pressure. And that pressure force is drawing the fuel from this sump. I should just say, obviously, the question does ask to find the diameter of this injecting tube. And we're given a required mass flow rate. Everything in orange here is to do with the fuel side. At the moment, we're working out the differential air pressure. So this Q doesn't relate to the air. It relates to the flow rate through this nozzle. Okay, and it has a coefficient of discharge of 0.9, which again, hopefully you're aware now that these sort of numbers are balancing parameters or balancing terms for Bernoulli. So usually both sides will balance in theory for an inviscid fluid. In reality, often we're dealing with a real fluid, non-inviscid or viscous flow. So what we can do is we can chuck in a correction factor on one side, and that's very much what a coefficient of discharge is. So this accounts for the small amount of mechanical energy that is actually lost. Obviously Bernoulli states that doesn't happen, but in reality it does. So that's what the coefficient of discharge is. But that comes in at the back end of the problem. Okay, so we don't have enough information on the fuel side yet, but we can work out this differential, this driving pressure. Obviously we have two unknowns. Sorry, we don't know U2, but what we can do is again use continuity. So Q equals UA. So we can write, we can rearrange this. U2 equals U1 A1 over A2. So we can substitute this in here and then rearrange the whole lot. So that goes in there, and then we can rearrange this expression for P1 minus P2. Okay, we've got our area ratio here. It's A2 over A1. Again, make sure if you're given an area ratio that you get it the right way around. Okay, so the area here is smaller than it is at the inlet. So we can start to, well, you can either put the numbers in straight away or you can rearrange the expression first. It depends on your particular way of working. Sometimes putting the numbers in and cancelling those is a slightly safer strategy, but it's entirely up to you. Whoops, -1. Okay, plug the numbers in. Remember, this is on the air side, so this row here is 1.23. That's a well, again, that's the inverse of the area ratio, and then we know U1 is 50. So if we work that through, delta P equals 1196 newtons per metre squared. So that's our pressure force, the differential pressure that's driving the fluid out. So we've worked that out. That's fairly easy to do. Now we've got to understand what we do with that value. What we can do now is apply Bernoulli in two slightly different locations. So we're going to apply it here at the outlet, and we're going to apply it here. The key thing to understand here is this is on the same streamline. We can't apply Bernoulli between here and here because they're not on the same streamline. So air is passing through. There's no kinetic term coming down here. This is just the pressure force. And remember, P1 acts all along this duct where it's at the constant cross-sectional area with area A1. So the pressure here is the same as it is here, okay? But there is no kinetic term. This fuel is not moving in this region. We're assuming that this tank is reasonably large. So there's negligible kinetic energy, negligible flow in this body of fluid until it gets up to this very small cross-section and exits with some velocity there. Okay, so this is the next stage of the problem. So I'm going to wipe the board off, pause the recording, and think about how you apply Bernoulli between those 2 points. Right, so it's actually an incredibly simple expression if we apply Bernoulli on the fuel side. So the only type of mechanical energy you have here at point 1, we'll call it 1 just for continuity, is the pressure. So P1, and then the stream tube's coming up through here. So equals the pressure in this region. Again, it'll be the same as the pressure here. So effectively applying Bernoulli just outside of that tube. So P2 plus half rho, again rho of the oil now, we'll call it U2 squared for sake of argument. It's not the velocity here, it's the velocity coming out of that jet. In fact, we'll call it UD for this diameter, because ultimately that's what we're asked to find. Okay, we need to rearrange now to solve for U. Again, if we can get an expression P1 minus P2, then we have that value already. It's 1196 newtons per metre squared. So It's a fairly simple expression. We have to apply now this discharge coefficient as well to the velocity. Okay, so if we rearrange that and add in the coefficient of discharge, so you do two, sorry, 2 goes up there. Oil. Okay, so you can plug in the numbers 0.9, 1196, and we're given the relative density of 0.7, so 700 kilograms per meter cubed in here. So put the numbers in, and we get 1.66 meters per second. Now we can go back and use the continuity equation. Okay, so we have Q, 125 cubic centimetres. I can't quite remember from the question, but it's 1.25 times 10 to the minus 6 meters cubed per second. Rearrange this, you can find the area, and then from that, pi d squared over 2, you can then work out the diameter. So if you want to write that in the full expression, this is what it is. Put all of the numbers in, and that equals the answer in the book, which is 9.8 times 10 to the minus 4 meters, or 0.98 millimeters. And you'll notice that's a very small number, and it is literally, again, sort of needle type injection. Carburetors are very old now. There used to be a sort of a valve here that would called the throttle that would pivot and would basically change this pressure imbalance or pressure difference to draw different amounts of fuel. It was a sort of a slightly passive system, but then if you had a cold day, cold air, you'd actually have what's called a choke, so some manual override for this. So it meant pulling a sort of a knob and a lever out of the dashboard. Nowadays, this is all done, it's an active system. It's called fuel injection. So the sensors studded around this part of the engine that sense temperature, density of the air, and then basically actively inject the fuel into the air mixture, and create a fuel mixture. So it's done very differently now. This is very old style, so I don't think there's probably very many cars, apart from classic cars, that have this sort of system on. Okay, so that's a brief overview. So again, we've applied Bernoulli twice here, and it's very important to think about the streamlines and where you can apply Bernoulli between. Okay, so we worked out the differential pressure based on the information on the air side. That was easy, and then we had to square it with ourselves, try and understand that here we have a pressure, but also a kinetic term of the air. We now apply Bernoulli on the fuel side, between here and here. That pressure, P1, still exists in here. You can see on the diagram there's an inlet. Okay, so that pressure is acting in this region. Okay, so it's acting down, pushing down on the fuel. But we've assumed that there's no kinetic term here. There's nothing in the question to suggest this fuel in this sump is moving. We're not given any information. You can't just pluck numbers out of thin air. So then we applied Bernoulli on the fuel side between here and literally just at the end of this nozzle, injector nozzle. So we have a pressure, energy here, but no kinetic term. And here we have, again, P2 acting in this region, where we have this cross-sectional area, plus the kinetic term of the fuel, okay, which we called UD. Again, rearrange to solve the one unknown, get our velocity, and then apply continuity to work out the area and then hence the diameter. Okay, so hopefully you followed that through. So the hardest part is to work out where to apply Bernoulli from, but it has to be on two cross sections of a stream tube or through a stream tube. Okay, hopefully that's helped you, and good luck with the rest of the problems.